alkenes are inherently nucleophilic and basic. This means that treating an alkene with a strong acid can lead to proton transfer from the acid to the alkene, creating a carbocation, which is then typically attacked by a nucleophile to give some product of addition of H and the nucleophile across the atoms of the alkene. We saw this general paradigm in hydrohalogenations, where HBr or HCl are adding across the alkene. But we can also add H and OH across the carbons of an alkene in a reaction called hydration. And acid-catalyzed hydration uses a simple mineral acid, something like H2SO4, in catalytic quantity, less than a full equivalent, along with water to cause this reaction to go. Because a strong acid is used, and that's highly analogous in reactivity to HBr and HCl, we'll notice a lot of parallels between acid-catalyzed hydration and hydrohalogenations employing HX. For example, Markovnikov regioselectivity is observed. In acid-catalyzed hydration, an H and OH add across the carbon-carbon pi bond, and OH adds to the more substituted position, and H adds to the less substituted position in unsymmetrical alkenes like this. Now, in these reactions, we may represent the acidic conditions in a variety of different ways. You may see a specific acid like H2SO4. You may see H3O+, indicating an acid in water. You may see H+ in brackets, used to represent the acid catalyst. There are a number of different ways and conventions for representing aqueous acid, but that's essentially the reagent we're using here. The counter anion, the conjugate base of the strong acid, is just an innocent bystander in this reaction, which is why H3O+ is frequently just written here, because the anion is a complete spectator. The rate of this reaction depends dramatically on the substitution pattern of the carbon that ends up linked to the hydroxyl group. For example, if we kind of set ethylene, C2H4, as our baseline here, we'll see that if this is the relative rate of 1, we get 1,000,000 times faster when we replace one of those H's with a methyl group. 2 methyl groups leads to a factor of 10 to the 11th. What is that? That's 100 billion times faster than the acid-catalyzed hydration of ethylene over here. So dramatic increase in rate as we increase the substitution of the carbons involved in the carbon-carbon double bond of the alkene. We can use the mechanism to explain this rate observation as well as the Markovnikov selectivity, and as you may have already guessed, with an acid in the presence of an alkene, a carbocation intermediate is going to be involved. In the presence of aqueous acid, the alkene can be protonated because it's a mild base, and this generates a carbocation intermediate. This occurs with Markovnikov selectivity for the more stable, more substituted cation in acid-catalyzed hydrations. And this also, notice, generates a nucleophile. Water has been generated, and water is a nucleophile that's certainly good enough to attack the ravenously electrophilic carbocation. But before we just blindly add water to the carbocation, we want to think about rearrangements here. Beware of rearrangements of this carbocation, which will happen very rapidly if we can generate a more stable cation via 1,2 rearrangement. In this case, that won't happen. Water will engage in nucleophilic attack at the cationic center, and we end up with a new oxygen-carbon bond. This is almost the alcohol product, but to get to the final product, we need to deprotonate at the nucleophilic oxygen, and that can be done via another water molecule. One interesting thing to notice at this point is this is exactly what makes the reaction catalytic. In the last step, we have regenerated H3O+, and that regenerated H3O+ can find another molecule of alkene and restart the catalytic cycle, engage in another iteration of the catalytic cycle. So the overall picture here is we protonate the alkene, generate a carbocation intermediate. This also generates a good nucleophile in water, which attacks the cationic carbon, and we lose a proton from that nucleophilic oxygen. This gives a neutral alcohol and H3O+. So acid-catalyzed hydration is a great way to convert alkenes into alcohols with Markovnikov regioselectivity. Notice that the OH ends up linked to the more substituted carbon in this case, and the new hydrogen, which was added in the proton transfer step, ends up at the less substituted carbon of the alkene. The clever will notice that this reaction is the reverse of the acid-promoted elimination of alcohols to give alkenes that we saw previously in the eliminations unit. I can treat this with acid, with concentrated sulfuric acid, to recover the alkene. So we have this question now of the position of equilibrium. What's favored, the alkene or the alcohol? I actually deliberately drew all three steps with reversible arrows because all three steps can be reversed depending on the reaction conditions. And the next slide makes this point. In going from the alkene and water to the alcohol, well, that's an addition process, right? And in going from the alcohol back to the alkene and water, that's an elimination process. And as it turns out, the use of dilute sulfuric acid, which contains more water, right, relative to sulfuric acid, favors the alcohol, while the use of concentrated sulfuric acid, which contains less water, is going to kind of pull the reaction this way, promotes elimination. Concentrated H2SO4 like this is actually commonly used as a so-called dehydrating agent, pulling water off of various types of organic functional groups. Alcohols are just the tip of the iceberg here. But in some ways, it's a Le Chatelier's principle kind of idea, where if we concentrate the H2SO4 and remove water in the process, that will promote the side or encourage formation of more of the side with water on it, right? So concentrated H2SO4 does elimination. Dilute H2SO4 in the presence of an alkene will do this addition process. Now, just as in hydrohalogenations, the stereochemistry of acid-catalyzed hydration is pretty much entirely random. So if we have an achiral carbocation that's generated via proton transfer, water will attack this cation from above and below with equal probability, and we get a racemic mixture of chiral alcohols starting from an achiral alkene in acid-catalyzed hydrations. When diastereomers conform, we expect an unequal mixture of syn and anti-diastereomers, but there's no simple way to predict whether the syn or anti-diastereomer is favored in these reactions. As usual, in reactions involving carbocations, we need to watch out for carbocation rearrangements here. For example, a carbocation rearrangement explains how this 4-membered starting material gets converted into a 5-membered product, and OH links up with a carbon that actually appears to have no further ability to pick up an additional group in the starting material. So to explain this result, let's start with what we know to be the first step of this reaction, protonation of the alkene with Markovnikov selectivity, generating the more substituted, secondary in this case, carbocation. If that were attacked by water and then a proton were lost, that would give this secondary alcohol. This is not observed. The major product is over here. And this comes from a 1,2 rearrangement of this cation from secondary to tertiary with ring expansion. We can open this 4-membered ring to a 5-membered ring by migrating one of the carbon-carbon bonds in the ring like so. So this 1,2 rearrangement leads to this carbocation. And notice this carbon that originally had 4 bonds now only has 3 and is positively charged. And this is the carbon that picks up the OH group in the final product. So now water engages in a nucleophilic attack on that cationic carbon. We end up with this structure, and deprotonation at the future alcohol oxygen generates the neutral alcohol product. So overall, it's the standard mechanism for acid-catalyzed hydration, proton transfer, nucleophilic attack, and proton transfer, but with a 1,2 rearrangement sneaking in the middle here, going from a secondary to a tertiary carbocation. And remember our adage so far in the course that when a carbocation can engage in 1,2 rearrangement to form a more stable carbocation, it will do so. Carbocation rearrangements can be very inconvenient and annoying. What if, for example, we wanted this secondary alcohol as our product? We wanted Markovnikov selectivity without carbocation rearrangements. Maybe we wanted to study what happens when I put a cyclobutane adjacent to a secondary alcohol group like this. Well, we couldn't make that via acid-catalyzed hydration due to this carbocation rearrangement issue. But a solution to this problem can be found in the Oxymercuration-Demercuration reaction, which is a Markovnikov hydration that occurs without carbocation rearrangement because a carbocation is not involved in the mechanism at all. And I did want to talk through the mechanism because the mechanism of this reaction is analogous to what occurs with halogens, which we'll see a little bit later, reactions of halogens with alkenes. So the difference here is that while mercury is a Lewis acid, mercury 2 acetate, which is the reagent in the first step here, is a Lewis acid rather than a Bronsted acid, and it's a pretty mild Lewis acid, to be honest. It engages in a kind of funky electron flow with the alkene. The alkene donates a pair of electrons to the mercury donates a pair of electrons back to the alkene, and an acetate, ACO here, is lost. And the intermediate that we form here contains a 3-membered ring with mercury in it, something along these lines. We've got mercury linked to the 2 carbons of the alkene, and then there are the substituents that the alkene was linked to over here. So we have the cyclobutane ring and the methyl, and this mercury is still linked to an acetate group, and it now has a formal charge of +1 at the mercury. So in a sense, in doing this, we've actually made the alkene somewhat electrophilic. Since the mercury is positively charged, we can imagine this mercury acting as a leaving group. And this is where water enters the picture. Water enters the picture now and attacks this so-called mercurinium ion, which is the name of this cyclic structure here, at the more substituted position. This is the position with greater partial positive charge because it is more substituted, and this leads to the formation of a carbon-oxygen bond at that more substituted position, which is what we wanted, right? This is Markovnikov regioselectivity with the nucleophile attacking at the more substituted position. So we'll end up with water here. I'm going to draw one of these OH bonds out explicitly because we're going to deprotonate there in the very near future. And we still have this HgOAC group here. And you can imagine what will happen next is loss of a proton. And just to save a little bit of time here, I'm going to copy and paste this without that acidic hydrogen in there. Let me see if I can just grab this. And this neutral alcohol then is what's generated at this point. But it's not quite an alcohol because we still have the metal, we still have the mercury attached to the substrate. What happens in the second stage of the reaction through the use of this reagent NaBH4, which is sodium borohydride, is replacement of the HgOAC group, which is still in this reactive intermediate really, with an H, so that the net result is hydration. And this is where the demercuration bit comes into play. So the overall process here is Markovnikov addition of water and mercury first, with the Lewis acid ending up linked to the less substituted position, and the nucleophile ending up linked to the more substituted position, followed by loss of a proton. Let's make that clear that a proton is lost here, and demercuration with sodium borohydride. This results in Markovnikov hydration with no rearrangement. I see no discrete carbocations in this entire mechanism. With a lack of carbocations, no rearrangements take place. So we can reliably add OH to the more substituted position without having to worry about rearrangements. Now, to close, oxymercuration-demercuration is a reaction that definitely has fallen out of fashion in recent years because of the use of mercury, which obviously has some issues with toxicity. So there are other ways, other more advanced ways to do these kinds of hydrations without rearrangements. But oxymercuration is, I'd say, mechanistically illuminating. It's one reason we still teach it. We're going to see, for example, 3-membered cyclic intermediates like this in halogenations of alkenes that behave very, very similarly to these mercurinium intermediates.